Hello everyone, welcome to another video of the course. In this video, we are going to solve the problem 9 and so on, depending on how much time we have today. So let's start. Here is the problem 9. The toroidal core shown in this figure is made from cast steel. The material of the core is cast steel, and we have the BH curve of the cast steel here in this figure of the reference, and the cross section of the core is circular. Okay. A. Calculate the coil current required to produce a core flux density of 1.2 Tesla at the mean radius of the toroid. So, the aim is to have this flux density in center. How much should be the value of coil current? Let me generate a new project in ANSYS Maxwell and save it. Problem 9. Okay, I want to visualize this problem. So add a 3D model and let's generate the geometry together. We have a toroid with circular cross section. The inner radius of the toroid is given here, and this is the outer radius, 6 centimeters, 10 centimeters, and this is the average radius in the middle of the toroid in center. So how we can create the geometry of the toroid? In ANSYS Maxwell, here you can see the X, Y, Z coordinate system, the global coordinate system. Let's select the active work plane XZ, right? Set XZ plane as active 1 and draw a circle here. Let's set its radius. This is actually the cross section of the core. So we know that the center of this circle is R average. Let's press enter. The R average is R1 plus R2 divided by 2. What is the value of R1? The value of the R1 is 6 centimeters. So this is 6. And the value of R2 is equal to 10 centimeters. So here I write 10 centimeters. And then what is the value of the radius of the core? If you consider this cross section, we know that the inner radius, this is R1, and also this is the outer radius R2. So the radius of the core is R2 minus R1 divided by 2. So here I can set the radius of the core. Let's press enter. It is equal to R2 minus R1 divided by 2. Divided by 2, we have a syntax error. So let's press OK. This is the cross section of the core. Now I am going to generate the 3D model of the core. How we can do that? We can use the sweep command. So here you can see the XZ plane, and if I select this face circle 1 from draw sweep, I can select this one, sweep around axis. Around which one? Around Z. What is the angle of sweep? Consider full sweep 360 degrees. So this is the geometry of the core, okay, that we have. Let's save. And now let's generate the geometry of the coil. How we can generate the coil geometry? Again, the active work plane is XZ. Let's draw a circle here. Set the center point equal to negative of R average. The radius R core, the radius of the core plus 2 millimeters. Let's consider this. And let me copy this circle. Let's draw another one. Again, here we have this. This is radius of the core plus 2 millimeter plus width of the coil. Width of the coil, let's consider 5 millimeters, okay, for the coil width. Now I can select this circle, hold the control key and select this one, subtract, okay. So if we sweep this face, we can build up the geometry of the coil. We can generate a detailed geometry, but also we can consider a simplified one. Here, I can select this face and from the draw, sweep around axis, around Z. For example, I can consider 2 degrees. And in this case, as you can see, I have one turn, for example. So depending on the angle of sweep, I can set the cross-section area. Or even I can consider extrude instead of this sweep. So here, for this object, let's delete the sweep and just use the extrude case. From here, along vector, along this vector, for example, let's modify it along which one? 0. 2 millimeter and 0. Along y-axis. So this is one turn. Then I can select this and use this option. Duplicate mirror around axis. Around Z. How many? For example, 20. The angle, 2 degrees. Or let's consider a higher one. 4. Okay. So here we have this case. Okay. If I select all of these objects, change the color, We can see the geometry of the coil. But yes, this is a perfect geometry. We can consider that. In terms of finite element simulation, we should consider a simplified model for faster simulation. And I am going to modify this geometry and consider a simplified one. We can define excitations on this geometry. We can consider a number of turns. I mean, the total number of turns in our case is 200, and consider the excitations and so on. But how we can simplify the problem? Let's delete this duplicate around axis and this circle. Delete this sweep. Just I am going to consider this simplified model. Let's select this face, draw, sweep around axis, Z, consider 40 degrees. Okay, this coil. Then select it. Again, duplicate mirror, right, with respect to ZX axis. So here we can set the normal position of the mirror plane and finally unite these two objects. So this is the coil. This is the equivalent model. And in this case, we can consider this excitation. Here, let's select the coil. Here also we can change the name, coil. This is core. For the coil, we can select the coil object and section it with the XY plane, edit, surface section with XY. I want to use this cross section to define the excitation. So this face, let's separate it and delete this one, for example. So in this simplified model, I know how much is the amount of current passing through this region. Okay. So in this case, we can specify the amount of the current and solve this simplified problem. My aim is to calculate the field in center of this core. So again, let's select the XY plane, this one, and draw this circle, set the cover lines command, suppress, okay, because I want to have an edge object in center of the core. Its radius is R average. Okay, so this right edge in center of the core. How we can calculate the field on it? If we have this view, this top view, and let's copy image. Okay. Here, as you can see, when we excite the core, for example, we need to consider a direction for the excitation also. Here, let's copy this. This is the direction of the excitation. I'm going to build up a magnetic field in this direction. This is the x-axis and this is y. I want to have a magnetic field in this direction, B. So the direction of the current should be in this direction. And consequently, for this region, the direction of the current is out of the paper. For this one is into the paper. Okay, so the direction of the field is in this direction. This is out of the paper and this is into the paper. For this integration path, if we use this equation, integral of h dot dl, we can write h times the length of the flux path in the center is equal to Ni. And finally, we can calculate current. Okay, so this equation, H center times the length of flux line in center is equal to Ni. And finally, we can calculate the current. But we did one assumption here. The value of the H is constant, right, inside the toroid. Is this assumption correct or not? Because this integral, right, simplifies into this term. So how we can calculate the current for the cast steel material to build up 1.2 Tesla? We need to use this HP curve. If we want to have 1.2 Tesla inside the core, 1.2, the value of the H for the cast steel material is equal to 1000. Okay, so we can interpolate the value of the H from this curve. Here you can see the MATLAB code. We have these inputs, the permeability of the air, the inner radius, outer radius, the number of turns, and the magnetic field intensity in core. Interpolated, right, considering B core equal to 1.2 Tesla for the cast steel material. So this is the value of H core, and this is the R average, R1 plus R2 divided by 2. This equation. And finally, we can calculate the current, the required coil current for part A of the problem. So if we apply this current to the coil, we can have 1.2 Tesla in the core. Let's try the same thing in the ANSYS Maxwell software. But in ANSYS Maxwell, we don't have this material. And I am going to consider this material and like before, export the HP curve in MATLAB and interpolate the data. So select the core and set the material to steel 10, 10, this material. So here you can see the properties of the steel 1010, the HP curve. Okay, you can export the HP curve in tab format on desktop, and here is the HP data. I also wrote this problem 9 modified. So this solution is versus the reference considerations, assumptions, and this is the modified one. We used our material that is available in ANSYS Maxwell. So this is the BH, data. So here are inputs. We have this desired value for core flux density 1.2 Tesla. How we can calculate the value of the coil current? If we have BH data, we can calculate the magnetic field intensity in core using this inter1 function. But in this case, consider that we are going to interpolate the value of H. So first, we should write B data, X point, data point, and the X points that we are going to calculate data points on it. So I am going to interpolate the value of the H in the core. So here, if we are going to have 1.2 Tesla, this is the value of H core. And for this material, if I run this, the value of the current is equal to 3.2 IA. Here also you can see the operating point, right? 1.2 Tesla, the corresponding value of the H. So here is IA, the value of the current for the construction of 1.2 Tesla in the core. So let's try the counterpart example in ANSYS Maxwell. Here, I am going to define the excitation for this phase. The total value of the current is 200 times coil current. The value of the coil current is equal to 3.2 ampere, as we saw in MATLAB, and the direction of the excitation is into the paper, XY plane. So this is the excitation, and now I can draw enclosure and solve the problem. So here is the enclosure, cylinder 1. Let's change the transparency to 0.9. The radius equal to 120, height equal to 40. If we consider a big enclosure, the simulation time will be high for this 3D model. So this is okay, and we can confirm that the flux generated by this coil is included in this region. So here we can duplicate mirror it with respect to the Z, right, XY plane, and finally unite this enclosure. And as you know, like before, for the 3D ANSYS Maxwell model, in this type of problems, we don't need to apply the boundary condition. By default is applied by the software. And at the solution setup, everything is ready. We can solve the problem, analyze. So after finishing the problem, we can plot the graphs. What is the error we have here? Okay, the software cannot find the conduction path because I didn't set the coil material, that is copper. Yes, we didn't set the material of the coil. Analyze to calculate the field inside the core and how we can visualize the flux density vectors. Solution completed. We can select all volumes. Field B, B vector, yes. You can see the magnetic field inside the core. This plot, yes. As you can see, the direction of the field in the core is counterclockwise, depending on the direction of the excitation that we considered. So let's delete this and select the circle for plot the B vector here. As you can see, yes, we have these B vectors. You can see the variation of the B, right? The average is 1.2 Tesla, okay, here. So I am going to draw the tangential component of B along this edge. In the field calculator, we can select quantity B, transport it into cylindrical coordinate system, and you know that the second component of a vector in cylindrical coordinate system is tangential one. So let's select the second component and define BT. This is the tangential component of the B. So from here, we can plot circle for BT. What is the average value? Is 1.2 Tesla. Okay, great. Because we did this calculation considering those assumptions. Here, variation is little. If you click on this axis, you can set the minimum value equal to 0. So you can see this curve in the center of the core. Yes, considering assumptions and writing this simple M file, we can determine the value of the current that we need to build up a specified value of B in the core. So, the next part. How we can calculate the core flux? What is the core flux in Webers? Assume uniform flux density in the core. So we calculated B in center, excuse me, the H, and the B is desired one, 1.2 Tesla. If we consider a uniform flux density in core, simply we can write this. The flux is equal to B times A. A is the cross-section area of the core. What is the value? Is equal to pi times R2 minus R1 to the power 2 divided by 4. This is the area of the circle. So I implemented this equation here for the cross-section area of the core. And this is phi. 1.2 Tesla times A times 183 in milliweber. So if I run the code, here you can see the value of the phi, 1.5 milliweber. Let's check the numbers with the exact solutions in the reference. Here is 1.51. This is IA, 2.51. And what about our material? The value of the phi is the same. Yes, because the value of the B is the same. Can we calculate this number in ANSYS Maxwell? Let's try. How we can calculate the flux? As you know, to calculate the flux in the core, we can use this integral equation, this double integral. B dot dA. This is vector. On what surface? Here, we can select the core and consider the Z x plane. So if we section it with the zx plane, we have these two cross sections. Let's separate them from each other. Edit, Boolean, separate. This is cross section, separate one, and this is this one. We can calculate this integral, okay, on these two surfaces. Let's analyze the problem again and implement a field equation to calculate the phi. So here, let's delete this. I'm going to plot b vectors on this face, for example. So field b vector, okay. As you can see, we have this field inside the core. The value of the b close to the inner radius is 1.3 Tesla and close to the outer radius is 1.04. We have variation. We don't have uniform field, right? As you can see here, according to this equation, for the r values that are close to r1, the value of h is high and consequently the value of b is high. And when we increase the r, h is low and b is low. We have this variation. But according to the assumption here, the problem, assume uniform flux density. Just we considered the value of the b in center and calculated the phi. And now I am going to calculate the exact value using the finite element software in field calculator. Let's select the b quantity. As you can see, we have bx, by, and bz. We have this face, and according to this integral, we need to calculate b dot, this is n hat dA. This is the surface area element, and this is the normal vector of the face. B dot n is the normal component of the b on the face that we are going to calculate the integral on it. Thanks to powerful environment of the ANSYS Maxwell, we can do these field calculations easily in the software. So here, b, the unit vector normal, b dot, the unit vector dot, this is bn. Then we select, let me define this as bn. This is bn. Okay. Copy to a stack. This is bn. If I select this face, core section 1 separate, I can calculate the integral on it. This is the phi. Okay. This is the phi, this integral. So add phi. This is intrinsic variable in Maxwell. Let's use another name, phi, in the core. So now let's generate data table. What is the value of the phi in the core? Is equal to 0.014 or 1.5 milliweber. Yes, really beautiful how considering these assumptions are good even for manual design. Okay, and we calculated these numbers using the double integrals, calculation of the field, and so on. Another interesting graph that you can generate, you can plot the BT along the R to check the variation. Okay, so let me generate a 2D model for it and try. We can solve this problem in 2 dimensions also. How? Just on a cross section. Maxwell 3D, create 2D design. I want to take a cross section on XY plane. Yes, this is the cross section of this problem on XY plane. We have this coil, this core, and these two regions. This is the enclosure. We don't need this. We should separate the coil to define excitations for it. So yes, the color is this one. How we can solve the problem again? Here I define excitation. This is 200 times coil current in the negative direction. We have the value of the coil current here. And this is the, let me copy this. For this region, we can define this excitation. This is out of the paper. So we defined these two excitations. In 3D model, just we defined one excitation phase because this is a continuous object. Let me select the coil and plot the current density vectors. Yes, you can see the current density vectors. Perfect. Okay, so you can visualize this interesting graph to check if you are doing your simulation correct or not. Here in this 2D model, we did the setting, but we need to apply the boundary condition here, the vector potential. And now I can add a solution setup, solve the problem. So I want to draw one line here and a circle cover lines no in center of the structure to plot the field quantities. So let's solve, analyze the problem and check. The solution completed. Here are faces. B vectors. Okay. What about the flux lines? Flux lines. Yes, we have these flux lines inside the core. What about the amplitude of the B inside the core? Yes, we have maximum B right here and minimum B here. I'm going to plot BT like before. So from here, field calculator, select B, cylindrical. The second component is B tangential. Also, I need to, no, that is enough. So done. From here, the circle BT, we can plot it. What is the average value? Close to 1.2 Tesla. So let's set the minimum scale equal to 0. Anyway, here let's plot this graph for the polyline 1. As you can see, we have this variation, the maximum B, minimum B, the average value, right, close to 1.2. This is just because of interpolation, right? This is not important. So here, if I plot B vectors on this edge, polyline 1, B vector, you can realize this point. So now let's go for the next part of the problem. You can repeat the same simulations. If we consider an air gap in the core, a 2 millimeter wide air gap, determine the new coil current required to maintain a core flux of 1.2 Tesla. So we are going to consider one air gap, and in this case, the reluctance in front of the field is much higher. How much we should increase the value of the coil current to build up 1 point Tesla again? We know that it will be higher, but how much higher? Depending on the amount of the air gap, the amount of the air gap reluctance. You know that in this case, our equation is this one. We can write this equation again. Integral of h dot dl equal to ni, but we have h core, l core, h gap, l gap. So let me copy this to the design. I am going to consider one air gap here. So this rectangle, the position 0, -1, 0 millimeter. This is 2 times R2, not important. Y size is 2 millimeter. The thickness of the air gap is 2 millimeters. So let's select the core and this rectangle subtract to consider this air gap in the problem. In this case, we have the magnetomotive force drop on air gap. If we consider this equation, how much is the value of H gap if we consider 1.2 Tesla? Again, for the air gap, the value of H gap will be equal to 1.2 Tesla divided by mu 0. L gap is 2 millimeter, and finally, using this equation, we can calculate the coil current. I implemented this equation here. So let's run the code. As you can see, in this case, the value of the current is 12, right? The current for the part C of the problem, 12. You can see this number here. So IC divided by IA is equal to 4.8, 5 times higher than the previous one just because of this air gap. So you can realize that when we consider air gap, the value of the coil current will be increased, right, to 12. So we considered this air gap. Let's set the value of the coil current for our problem. Here is the code for the problem. In this case, the value of the I is 12.73. And let's analyze the problem for this 2D model. I want to explain one important point. So here, let me delete this first and select all objects, flux lines. Okay, here you can see flux lines, and if I increase the number of flux lines to, for example, 100, you can see this leakage flux lines. In this case, we have air gap, and you can see the fringing effect. Yes, in this equation, we didn't consider the fringing effect, and we considered the corresponding area of the flux similar to the core in air gap. But as you can see, using the finite element method, we calculated the exact solution, and we have these flux lines. So we can not get the exact value of the 1.2 Tesla in air gap. So here you can see the value of BT in core. The average value is 1.27 Tesla, still close to 1.2, but you can see these variations. Inside the coil here, so let me delete this. Select core, the BMAG. Here, if I add a marker, here the value of B is 1.34, but here is 1.17 different. And unlike the previous one, we have this pattern for the flux density. Yes, here because the reluctance of the air gap is high, we don't have the previous pattern for the B. And again, if I select this edge, plot B vectors, as you can see here, close to the air gap, we have both tangential and radial components. Okay, so these points are important in the real solution. But how much is the value of B in air gap? If I plot the BT in air gap, calculate the average value is 1.1 Tesla. So let's consider a fine mesh inside the object, 3 millimeter, and repeat the solver. I want to calculate BT with a better precision. So the value is a little bit lower than what we calculated here. Because of the fringing effect, this non-uniform effect of the magnitude of the B, and this equation is not necessarily true. This one, H dot dl, that we considered it H core L core plus H air gap. Yes, because here the value of the tangential component of the H along the circle 4 is not constant. So here, this is the polyline BT, excuse me, this circle 4. As you can see, the value of the B is not constant. However, the average value is 1.27. So this is the numerical solution, and this is the equivalent analytic solution, but results are close. The point is this: when we consider air gap, the value of reluctance is much higher, and we need this high amount of the current. And we can predict this current using this equation. However, using the finite element method, we can do parametric analysis, change this number, and calculate the B in air gap to find the value that we need. But the important point is that using analytic equations, we calculated closed numbers. Okay, so you don't need to consider high iterations in the finite element model to find the desired value of the B in air gap. You can compare the flux density plot in this case and in the previous case. Why we have this pattern? Okay, so you can practice this in the software. Even in the 3D model, also you can consider air gap and repeat the problem, generates the fields and compare. So I think this is enough for the problem 9. You can repeat the same things. You can consider also other materials, try calculations, and compare. So let's go for the next problem. Okay, problem 10. In the toroidal core coil system of this figure, the coil current is 2 ampere and the relative permeability of the core is 2000. Yes, the permeability is given. The core has a square cross section. Okay. Determine the maximum and minimum values of the flux density in the core. Yes. The magnetic flux and the flux density at the mean radius and compare it with the average flux density across the core. Yes. So let me save this project. We can save as this problem 10. For this 3D model, and the 3D model, if we consider a square cross section, the cross sections are the same, right? The 2D models are the same. So here you can see, like before, we will have maximum flux density for the inner radius and minimum here. In this problem, the permeability is given and we should calculate the minimum and maximum values of the B. So let's copy the code for the problem 9. This is problem 10. The value of the permeability is given. This is mu r is 2000 relative core permeability. The value of the coil current is given, I. This is the value of the coil current. Coil current, ampere. And we don't have air gap in it, right? We don't have air gap. Determine the maximum and minimum values. The core has a square cross section. Okay. So here we have the value of the current is 2 ampere. Let me delete this. Outputs, the R average, L center, we have This is the H mean. Minimum value of the magnetic field intensity is equal to N times I divided by, you know, 2 times pi times R2. This is the minimum value of H ampere per meter. So we can calculate the maximum value. The magnetomotive force is the same. This is max. This is maximum value of H. Also, we have permeability of the core, mu r times mu 0. This is the permeability of the core, Henry per meter. So we can calculate B mean is mu times H mean. This is minimum value of B. The unit is Tesla. We should consider times 1 e minus 2 here. This is in centimeter and centimeter. Finally, this is B max. This is H max. The maximum value of the B, excuse me. Okay, and let's delete this. So if I run the code, as you can see, the minimum value of B is 1.6 Tesla. The B max is 2.6. Okay, is this correct or not? Let's check. We consider these numbers. In the ANSYS Maxwell model, we should change the core material. Let's use the iron. The iron material that we used it before, not cast iron. This one with a simple constant permeability equal to 2000. Okay. The permeability, the relative permeability is given here. So here you can see the equations that we implemented in MATLAB for the minimum and maximum values of the B and H. And if I repeat this example, analyze, you can check the value of the B. Here, this is the value of BT. What is the maximum value? The maximum value is here, 4.2 Tesla. This is the minimum value, 2.56. We didn't set the value of the current. The value of the current is 2 ampere in this example is given here. So let's rerun the solution. The value of the BT. The maximum value is 2.67. 2.67. The minimum value is 1.6. 1.6. As we calculated it here. So let me set these coordinates exact. You know, sometimes this is just because of interpolation in ANSYS Maxwell that you can see this line. Anyway, I want to compare the curves that we consider here and what we consider in MATLAB. Now, here determine the magnetic flux in the core. How we can calculate the magnetic flux in the core? If we are going to be precise in our calculations, we can write something like this. We know that B is a function of R. Okay? So B is a function of R. And in general, we can write H is equal to Ni times 2 pi R. You can consider this a square cross section of the core. So in this case, let me delete this one. In the 3D design, we can modify the structure, or let's generate a new design. Save. I want to generate the model with the cross section that we considered in the problem number 10, the square cross section. So here we can draw one square, the position of the corner point. If you consider this x, y, we need the position of this point. This is our average. This is R1 and this is R2. So we know that this is R2 minus R1, this width. Okay. So here I can write this is R1 negative of width of the core divided by 2 and 0 for y. This is z because we are in the xz plane. R1 is 6 centimeters. Width of the core is R2 minus R1. R2 is 10 centimeters. And x size is width of the core, z size, width of the core. Okay, so we have this cross section, I think. Yes, R2 is 10 centimeters. We didn't set the value of the R2 correct. 610. The width of the core is 10 minus 6. That is 4. And we have a square cross section. So again, select, draw sweep, Z. This is the core, right? And we can draw two squares. One here. This is negative R2 minus 2 millimeter. And this is negative of width of the core minus 2. The x size is width of the core plus 4. And this is the same. This cross section. So here just I need to consider width of the core divided by 2. This cross section. Another one. Okay, this is divided by 2. We should minus this with width of the coil. and also this one. Width of the coil. Okay, so this is 4 millimeter, and let's copy this. Here I can write plus 2 times width of the coil. So rectangle and this rectangle, subtract again the Z, 40, duplicate, mirror again, 0, 0, and 0, 0, 1, and 0. Okay, so these two rectangles unite, change the color. This is the new problem. We can set the materials. This is the iron. Okay, so again we need to section to define the excitation in it. So here let's separate, delete this one, assign the excitation 200 times coil current. The direction is into the paper, xy plane. The coil current is 2 ampere. So this is the excitation, and at a solution setup I am going to calculate the magnetic flux in the core and compare with the finite element, and I am going to plot the value of B as a function of R, right? We know that B is a function of R. This is R. So here, select this core. Again, we need to calculate sections with the XZ plane. Separate these two faces. Draw the enclosure. 130, 40 for the enclosure of the problem. Okay, that is okay. So duplicate and mirror it again. You can see these two faces. Yes, this is correct. And unite. We don't need to apply boundary conditions. So we are ready to run the simulation and plot B. So analyze. I want to visualize the flux density vectors. The solution completed. Now this phase, the B vectors. B. You can see the B vectors on this phase. Okay. And the variation that we have. So consider this cross section. We know that for this strip, the value of the B is constant in the y direction because B is a function of R only. So this is H and B is mu. H is equal to mu Ni divided by 2 times pi times R. So how we can calculate the total flux? Using this integral. B dot dA is integral of is equal to double integral BR, the surface element area is dr, this one, times width of the core, that's all, from R1 to R2. Okay, so we have integration in the y direction, but we know that the value in the y direction is constant. So, but actually we need to consider negative of width of the core to positive, right? So we can calculate the integral in this format. And if you replace this, you can calculate the integral. Okay, so the phi is mu n I width of the core divided by 2 times pi integral of 1 r dr r1 r2. What is the value of this integral? Is natural logarithm of r2 divided by r1. Okay, so let's check for this problem. This is b. Let me write the final equation. Phi equal to the equation that we derived is mu times n times I times log natural logarithm r2 divided by r1 divided by 2 times pi. Here we have width of the core, that is r2 minus r1 times r2 minus r1 times 1e minus 2. So what is the value of the flux? 3.3 milliweber. Okay, so let's check if we can calculate this number, 3.3 milliweber in the FEM. So again, in the field calculator, like before, you can select B, the unit vector normal dot, this is Bn, the geometry, this section, and calculate integral. So this is the y in the core. So here in the data table, yes, this is 3.3 milliweber. Perfect. We calculated this integral and calculated the flux, and using this equation here, what is the value of the b as a function of the r? You know, if I consider this r line space, I'm going to consider from r1 to r2, consider 1000 points. The value of h as a function of r is n times I divided by 2 times pi times r. So this is dot division. We need to consider a dot here. And finally, b as a function of r is mu times h. So we can plot r and b as a function of r. So you can see we have this variation. So we can write x label is r The unit is millimeter. The unit is millimeter. This is the X label. The Y label is B. The unit is Tesla. Okay, so here I can consider this times 1e minus 2 to have it in meter, and here time y 1e2 to have it in centimeter, excuse me. So let's check the value of maximum B, the minimum, and in the title I want to write sprintf the B average is equal to, you know how to calculate the average value of the B as a function of R. The average value is 2 Tesla, the average value of this graph. And we have this variation. Perfect. So what is the part C? We calculated the flux using this equation, using the ANSYS Maxwell, and compared they are okay. But in the part C, we should calculate the flux using the average value of the B. Determine the flux density at the mean radius of the core of the toroid and compare it with the average flux density across the core. Here, the variation is not linear, as you can see. If I hold on, box on, and grid on, and directly connect plot. I want to connect the first point and end point in the graph, so I can write R. I'm going to just pick up the first point of the radius and the last point. So here I can write R1 and R end. Okay, and here consider BR, the first value and the last value. Let's use the red color to connect the points directly. What is the error? So this is just a grid, I think. Hold on, grid on. Okay, so as you can see here, we have the blue one is the exact solution, that B is a function, of R. So in the part C, we should determine the flux density at the mean radius of the toroid and compare it with the average flux density across the core. So the B in center, if we are going to calculate the B in center using the equation that we have, the value is 2 Tesla. The average value, what is the average value across the core? Is 2 Tesla again. Okay, so can you realize this point? But if we consider a linear variation, right, the average is different. The average is different. So yes, you can calculate the flux density, the you can calculate the flux using this equation, B center times area, and compare it with the exact equation that we used here to calculate the phi. This is the flux in the core, milliweber. We can multiply this by 183 to have it in milliweber. So this is one method. And if I consider the average value of the B, this, so this is phi using the average numbers. The average value of the B, or the B center here, R1 is 6, R2 is 10, and the R in the center is 8. The value of the B for the center is 2 Tesla. Okay, the average value. So if you consider the mean value times the area, this is the area, 1e minus 4, this is to the power 2. This is the flux in the core using average values, or using B in center. So let's run. Here you can see the value of the phi. Here is available this number. You can compare it with this number. We should multiply this by 183 if we are going to have it in milliweber. And as you can see, we got the same numbers. So considering the B in center is a good approximation, and this is the outcome of this question. Okay, so you can consider the value of the B in center. Here this is the L center, this is the B center, and you can calculate the flux in the core using the average values. Also, you can use the equivalent circuit method. This is the value of the reluctance, and calculate the value of the B using the magnetic equivalent circuit and compare. It's not too complex. Here I have the equations in this slide. So you can use these equations and try to calculate and practice, compare. These two problems, right, were very good. Problem 9 and 10, toroid with different cross sections. We can realize different important points from these two questions. You need to do it yourself. You can change numbers, even change the material in the FEM, compare, and investigate these points for other cases. Okay. Anyway, I think it's enough for this video, and let's continue solving the next problems for the next video. Thanks for watching.